Good afternoon, dear participants. We had come to the last day of the faculty development program, Avant-garde Friends in Mathematics. It's my pleasure in introducing the resource person for the day, Dr. Madeleine, Department of Mathematics and Physics, Faculty of Arts and Science, Lebanon International University, Lebanon. She had published quite a number of research papers in international and national journals. She had been a recipient of awards and recognition like Honorary Rosalind Member of London Journal Press in the year 2020. And she has also received a recognition as Certificate of Excellence in Reviewing in recognition of an outstanding contribution to the quality of journal, International Journal of Nutrosophic Science in the year 2020 April, as well in the year 2017. And she's also the member in the editorial board of International Journal of Nutrosophic Science. She has also been the reviewer for the following journals like Algebraic Structures and Their Applications, Mathematical Methods in the Applied Sciences, Journal of Mathematics Research, Nutrosophic Sets and Systems, Journal of Algebra and its Applications, Iranian Journal of Mathematical Chemistry. Now I would like to invite the resource person of today to take over the platform and deliver her address of the content to our participants and make this day a wonderful day. Thank you.
Okay, hello everyone. I hope all of you are safe and well. I'm Madeleine Tahan. I'm a researcher in the field of hyperstructure theory and its applications. First, it's my pleasure to be a part of FDP program in the Trends in Mathematics. As a resource person, I'd like to thank the organizing committee for all their efforts for inviting me to be a part of this international event. And a special thank you goes to Dr. Pari for all her follow-up. I'm sharing now my screen. Please let me know if you are able to see it or not.
Yes, yes.
Are you?
Yes.
Okay. Now, in this talk, we're going to be talking about algebraic hyperstructures and its applications to arithmetic functions. First, we're going to review some basic concepts about hyperstructure theory, including hypergroups, hyperrings, and HV structures. Also, we're going to discuss some fundamental equivalence relations on these hyperstructures. Next, we're going to present some applications of these hyperstructures to arithmetic functions. And finally, we're going to leave with some questions and highlight useful steps to solve some of them. By the way, if you have any questions that you would like to ask, you can just put it in the chat box, and I'm going to take a note about it and answer it at the end of the talk. Now, before talking about the theoretical part about hyperstructure theory, what about some real-life examples about this theory? We all know in groups or in algebraic structures like group, rings, usually we have two elements. These two elements under a certain mapping that we name it as an operation, they're going to reproduce a third element that is not necessarily a new element. For example, if we are adding two integers, we're going to get a third integer. If we are multiplying two integers, we're going to get a third integer also. Now we can raise this question. Is it necessary that whenever we have two elements under a certain mapping, is it necessary to get only one element? Actually, the answer is no. And we're going to represent some examples about them from chemistry and from biology. In a chemical reaction, all of us know that usually we have some reactants, two or more reactants. They're going to react together under certain conditions, and they're going to reproduce some products that they are not necessary to be only one product. For example, here we have the spontaneous redox reaction of astatine. We have AT2 and AT plus. They reproduce here AT plus and AT minus, and we do not have in the product just one product. This is regarding chemistry. Let's move now and talk about biology and some heredity. In Mendelian inheritance, we're going to take the case of incomplete dominance. What we mean exactly by incomplete dominance, it means that none of the alleles is recessive with respect to the other, and none of the alleles is dominant over the other. For example, if we have here a white flower, which is crossed with a red flower, in the first generation, all the flowers are going to be pink. Now, if we cross away these pink colors, these flowers that they are of pink colors, in the F2 offspring, or the second generation, we're going to be having red flowers, pink flowers, and white flowers. So again, they did not reproduce only one element. They reproduce, in this case, 3 different elements. Other examples we can get from the AB blood group. Here we put a table summarizing all the possibilities that we're gonna get. We have also an example from the RH blood system. Also, we put all the cases that we're gonna get. Now, I guess we are ready to talk about the start of this theory. So in 1934, the French mathematicians Frederick Marty, who was only 23 years old, defined the concept of a hypergroup, and the law characterizing such a structure, it was known as hyperoperation, and the whole theory, it was known as hyperstructure theory. Actually, Marty's motivation to introduce this new concept is that the quotient of a group modulo any subgroup that is not necessary to be normal of it is a hypergroup. Now, all algebraists or students, if we have some students here that took before group theory, know that if we have a group and we are finding the quotient of this group modulo its normal subgroup, we're gonna get a group under this operation, which is here. And we name it usually the factor group or the quotient group of G mod H if H is the normal subgroup. Now, in reality, if H is not a normal subgroup, it's just a group. It's not a normal subgroup of G, it's just a subgroup of it. We're not gonna get G mod H under this star, this mapping, we're not gonna get it as a group. This is because this mapping, it will not gonna be the Cartesian product of G mod H with itself to G mod H, it will be to power star of G mod H. Now, what we mean exactly by power star of G mod H, it is the set of all non-empty subsets of G mod H. And this one, we name it as hypergroups, the hypergroup that Marty defined. Now, to understand this idea, we put a simple example. Okay, let's move to the simple example that we put. Now, we know all that Sn is the symmetric group of n letters. We took here the example of S3, which is the symmetric group of 3 letters. We are taking it dot here, the operation dot, we are taking it as the usual composition of permutations. We wrote first S3 as transpositions. Here, 1, it is the identity. We know also that the very famous normal subgroups of Sn is An. So A3, it will be a normal subgroup in S3. A3, it's defined as the set of all even permutations, which are the identity, the transposition 1, 2, 3, and the transposition 1, 3, 2. It's a normal subgroup of S3. So from group theory, we can deduce that the factor group S3 mod A3 under this operation is a group. And of course, it's easy to see that this factor group is isomorphic to the group of integers under addition modulo 2. Now, what if we have a subgroup that is not normal? Let's give an example on a subgroup that is not normal. If you look here at M, it's defined as the identity 1 and the transposition 1, 2. It's, of course, a subgroup of S3, and it's not normal. This is why it's not normal, because M13 is not the same as 13M. Then, S3M, we can write it as these 3 elements. It will not be a group under this operation. And this is easily seen because if we take an element from S3 mod M and another element like M star 13 we're gonna get a set which is not an element in S3 mod in 1984. Here we construct Cayley's table for this hypergroup. If we look here, M star M is M star 1 free M. It's not an element, it's a set, and so on. Now we are done with the start of the hypergroup theory. Unfortunately, Marty's life was too short to continue researching on this very important topic. He died in 1940, just 6 years after he defined this, this new topic. And the theory knew an important progress starting with the 70s when the research area enlarged, more hyperstructures were introduced, like hyperrings, semi-hyperrings, more types of hypergroups like canonical hypergroup, polygroups, semi-hypergroups, hyperlattices, hyperfields, and so on. And many researchers, very important researchers in this domain, they worked on this theory and they are still working about on it, like Kirsten. This theory, it has applications in almost every field of science, like biology, chemistry, economics, and if we are talking about mathematics and computer science, it has applications in geometry, topology, analysis, group theory, code theory, automata theory, fuzzy sets, multisets, and the last applications for it, it was in philosophy, which is a very new topic in mathematics and computer science, and it was introduced in 1995 by Florentine Smaragdish. So let's now give some basics about this theory in order to understand what is left in this topic. So here we are defining something known as hypergroup point. By the way, algebraic structure, it's like a special case of hypergeneralization of algebraic structure. So if we have a group point, we can generalize it to get what? To get a hypergroup point. If we have a group, we generalize it to get hypergroup. If we have a ring, we generalize it to define hyperring, and so on. So if you want to read about this theory, every notion that is defined for algebraic structure is generalized for hyperstructures. So to define a hypergroup point, we are starting with a non-empty set, H, we name it in H. We define a mapping, which we take it here as circ. This mapping, it takes the Cartesian product of H with itself to the pair star of H. Again, what do we mean by pair star of H? It means all non-empty subsets of H. This one, H, with circ, we name it as hypergroup point. Now, how can we deal with the composition between two sets? It's defined in this way. So if you want to find the hyper operation between two sets in H, A, B, it's given as the union of A circ B, where A is an element in capital A and B is an element in capital B. Now, also, in a hypergroup point, we would like to define the identity, what we mean exactly by identities in hypergroup point. Now, we know that in a group point, an identity, it means if in case it exists, it means that it's an element in H such that E star X is equal to X star E, which is X. Here, we define the identity in another way. We define it as it's an element in H such that for every X in H, X should be in X circ E intersection E circ X. Okay. Okay, are you still seeing the presentation?
Yes, ma'am, but someone presented their own screen, so now it's gone. Can you resume your presentation again?
Okay.
Yeah, thank you.
Okay. Okay, are you seeing the screen now?
Yes, it's visible now.
Are you seeing the screen?
Yeah,
Okay,
it's visible
that's
now.
great. Now, let's go back to the identity. We are defining the identity as an element E in H, such that X is in X circ E intersection E circ X. Now, why do we have to define it in this way? This is because, as we going to define what do we mean by semi-hypergroup, quasi-hypergroup, and finally we're going to deduce what do we mean by hypergroup. By the way, for those who know a little bit about hyperstructure theory, here we are defining hypergroup of Marty because we have other types of hypergroups like canonical hypergroups, we have polygroups, and so on. And by the way, in some researchers, and especially old ones, they used to use, instead of hypergroups, they used to use multigroup. So here we are defining a hypergroupoid H circ. It should be a semi-hypergroup if the associative law holds. What do we mean by associative law? It means that this one is satisfied. I don't know whether you are able to see what I'm highlighting. So I'm highlighting here the associative law. It's X circ Y circ Z is the same as X circ Y, all of it circ Z. Now, to be a quasi-hypergroup, we need to prove that circ H is the same as H, same as H circ X. This axiom, we name it as the reproduction axiom. Now we can deduce, when can we say that it's a hypergroup? So to prove that it should be a quasi-hypergroup, it means that it should be satisfying the reproduction axiom. Also, we need to define what do we mean by subhypergroup. It's the same like the definition of a subgroup. So we know from group theory that we can name something as a subgroup if it's a group under the same operation. So here we are saying that a subset of a hypergroup is said to be a subhypergroup if it's under the operation or hyperoperation circ is a hypergroup. Now, in order to prove a certain subset is a subhypergroup, it's enough just to prove that it's a quasi-hypergroup. Again, what we mean by quasi-hypergroup is that it satisfies the reproduction axiom. Okay, sorry. Now, let's give some examples about hypergroups. Some of these examples, they are from references, either from books or articles from some colleagues or articles from for me. Now, the first one is from a book for Davos. Here, from a group, we can get a hypergroup. How? We are saying that for any xy in this group, we're going to define x circ y to be the set generated by xy. And in this way, choose another example. This is the third one, is a very important example. It's known as the biset hypergroup, and we name it as the biset hypergroup because the hyperoperation that we are using here is very, very easy. All what we have to do is just to define A star B as the set AB for all AB in H. By the way, every group, we can consider it as a hypergroup by considering the hyperoperation as the singleton AB. Okay, we have some more examples. We have also a very important example, which is known as the total hypergroup, and it's almost the easiest type of hypergroups because we are just defining the hyperoperation to be H for all elements. It means that it's the whole set. So if the set is finite and we wanna construct Taylor's table, we're gonna get here all the elements or the all these sheets, the shells that are here, we're gonna get them as H. Also here we have another example on 3 elements. Here we are saying that this one, by using this following table, it's a hypergroup. By the way, this hypergroup, it's a cyclic hypergroup, and cyclic hypergroup is a special case of hypergroups, but we are not concerned about it in this talk. Here we have some important remarks to discuss about hypergroups before moving to talk about hyperrings. First, we know about the identity in groups. It's what? It's unique. Now, identities in hypergroups is not necessary, or in hypergroupoids, they are not necessary to be what? To be unique. Why? If we take the example of the biset hypergroup, every element in it, it will gonna be an identity. But if the identity is a scalar identity, it will gonna be unique. Also, there is an important remark that we can find a hypergroup or a hypergroupoid that does not have an identity. Also, regarding subgroups, we know from group theory, if we have a group that is not trivial, it means that the number of elements in it is greater than or equal to 2, then it has at least what? At least 2 subgroups. This doesn't hold for hypergroups. We may be having a hypergroup that has exactly one subhypergroup, which is itself. And here we have an example. If we give an example on the total hypergroup, it doesn't have any subhypergroups except itself. And also the hypergroup that we just put here, this one, it doesn't have any subhypergroup except itself. Okay, we are done now with hypergroups. Let's move now and talk about hyperrings. So again, hyperring is a generalization for what? For a ring. To define a hyperring, we have to define 2 hyper operations, the +1 and the .1. In which R plus, it should be a hypergroup. Again, what we mean by exactly by hypergroup is that it's a quasi-hypergroup. It's also a semi-hypergroup. And we need, all what we need about R dot is to be semi-hypergroup. Also, we need that to be distributive with respect to plus. What we mean by distributive, it means that if we have 3 elements, A, B, C, is the same as A dot B, B plus A dot C. Here we have some examples about hyperrings. This is a hyperring of 2 elements. The plus, if we look here, is a hyper operation. The dot is an operation, but we have the right to put it as an operation. Also, here we have a very hyperring. One more example, 2 more examples about hyperrings. Here we have a hyperring of 3 elements. It's defined by the following tables. We have to put a table for the plus and a table for the dot. Also, another example, we can start with a ring and get a hyperring. How? If we started with R plus dot as a commutative ring, what we mean by a commutative ring, it means that the dot operation is commutative. And by setting R bar to be the set of classes, X bar, each X bar, it contains minus X and X, we can define hyper operations plus and cross in this way. If you look here, the hyper operation plus, this is a hyper operation, whereas this one is, it's only 1 element, so it's an operation. Then the whole system, it will gonna be a hyperring. In order to illustrate this one, we're gonna illustrate it via this example. We all know that the ring of integers under addition modulo 4, under addition and standard multiplication modulo 4 is a ring. So 0 bar, it's equal to what? 0 and minus 0. If we go back to the previous slide, it's 0 and minus 0 and 0, which is 0. And 1 bar, it's 1 and minus 1. Minus 1 with respect to Z4, it's 3. And 2 bar is 2 and minus 2. And minus 2 with respect to Z4 is also 2. So Z4 bar is 0 bar, 1 bar, 2 bar. And here we can construct their tables. These under these conditions, or the following tables, they're gonna give the bar of Z4 under the operation plus and the new operation multiplication as a hyperring. So we are done now talking about hyperstructure theory. Now we're gonna move to talk about a generalization of HV structures. HV structures, they were introduced by Vagiaklis in 1990 as a generalization of the known algebraic hyperstructures. So if we have hypergroup, we're going to be having weak hypergroup or HV group. If we have a hyperring, we're going to get HV ring, or we name it as weak hyperring. Now, why do we name them as weak hyperstructures? Because in hyperstructures, in the axioms, we have equality. For example, in the associativity, we have equality. In the distributivity, we have equality. Whereas here, we're going to be replacing some or all of the axioms by, instead of equality, we're going to replace them by the non-empty intersection. Now, why did Vagelos introduce the notion of weak hyperstructure? We know all that a group modulo a normal subgroup of it, we're going to get a group that is known as factor group. We know also, according to Marty, that a hypergroup modulo a group modulo any subgroup of it is a hypergroup. Now, Vagelos noticed that if we have a group and we found its quotient with respect to any of its partition, we're going to get an HV group that is not necessary to be a hypergroup. In fact, this class of hyperstructure is a very large one. It has lots of applications, and the first application that Vagelos worked on it was in representation theory. So here we have an illustration for what Vagelos said about the HV group when he defined it. Again, we are taking the group of integers under addition modulo 4. We're gonna get a partition of it. If you look here, this is a partition for Z4 according to this equivalence relation. And by finding the quotient of Z4 mod this equivalence relation or mod this partition, we're gonna get this table. This one, if we look at it, it will not be a hypergroup. Why isn't it a hypergroup? If you look at this axiom, the axiom of associativity here, it's not satisfied. Why it's not satisfied? Because if we take 0 bar star 2 star 2, we're gonna get 0 bar 2, which is not equal to 0 star 2, all of it star 2. And of course, this one, as we said before, because the associative law is not valid here, it's not a hypergroup. We have other examples. But before giving some examples about HV groups, let's put the formal definition of it. Here we are defining what do we mean by HV semigroup. It means that the associative law is weak, the intersection is non-empty. And to name it as an HV group, it should be a quasi-hypergroup. What we mean by quasi-hypergroup, it means that the reproduction axiom is satisfied, and it should be also an HV semigroup in which the associative law, we have the weaker part of it. Here we have the example of Vagelos in one of his papers. Okay, we have here another very interesting example. If we take the ZMN is all, it contains all integers modulo MN, and of course M and N are positive integers. We are saying that ZMN under star is an HV group, and star is defined in this way. We are defining it as x star y is 0m if x is equal to 0 and y is equal to m. Otherwise, it's x plus y. Of course, what we mean by x plus y here is x plus y modulo mn. To illustrate it, we put this this example when m equal n equal 2. So only, as you look here, only in this this one, 2 star 2, we're gonna get 0, 2, and everything else we're gonna stay as C4. By the way, this type of HV group, we name it as very thin HV group, because if you look here, everything in the table is what? Is only one element, except we have one entry in the table in which we have more than one element. Very thin hypergroups or very thin hyperstructures, they are very important in many fields, and we have many papers about them. But again, we are not concerned about them in this talk. Okay, here we have one more example on a commutative HV semigroup. By the way, to say that a hyperoperation is commutative, we should be having A round B is equal to the same as B round A. And again, this hyperoperation is a semi-hypergroup, is not semi-hypergroup, and not also a quasi-hypergroup. So it's not an HV group, it's just an HV semigroup. Now we are done with defining HV groups. We can define HV ring. So in an HV ring, we have two hyperoperations in which R plus, it should be an HV group, R dot, it should be an HV semi-group, and dot, it should be weak distributive with respect to plus. What we mean by weak distributive with respect to plus, it means that A dot B plus C intersection A dot B plus A dot C is the non-empty set. And to say that a certain HV ring is commutative, we should be having the two hyperoperations as commutative. Here we have an example. Starting with any HV group, we can define circ in this way, x circ y equal to xy, and we're gonna get h star circ as an HV ring, and we already illustrated it in slide 30. So here we took H to be 0, 1, 2, 3. This is an HV group. It's the same as the HV group that we just found here in this slide. And dot, we define it as 0, 1 is 0, 1, 1, 1 is 1, 1, is 1, 1, 2 is 1, 2, and so on. So we are now done with the definitions of hypergroups, the definitions of HV structures. We can move now and talk about fundamental relations, which are special types of equivalence relation. We're not going to go into details about fundamental relations because we have other things to talk about, arithmetic functions. So just I'm gonna put the definition of a strongly regular relation. If we have a semi-hypergroup and R is an equivalence relation on H, what we mean by equivalence relation on H, it means that it's reflexive, symmetric, and transitive. We can say that AR, we have here two lines above it. What we mean by it, it means that for every element in A, which is small a, and every element in B, which we take it as small b, in case we have A or B, we should be having A or B. It means that every element in A should be related to every element in B. Because of this condition is very strong, we name this relation a strongly regular relation. So to be a strongly regular relation on the right or on the left, whenever we have X in H and A is related to B, we should be having A circ X strongly related to B circ X, and of course from the left it should be the same. To be strongly regular in general, we should be having it strongly regular from the right and strongly regular from the left. Here we have a very important theorem. If we are starting with a hypergroup and R is an equivalence relation, a necessary and sufficient condition for R to be strongly regular is the quotient H mod R. It means that the hypergroup mod, the equivalence relation of it should be a group. Now, the fundamental relations, they're gonna transform us from algebraic hyperstructures to algebraic structures, and we can consider them as the main tools connecting the class of hyperstructures, or of course the weak hyperstructures too, to the classical algebraic structures. Now, what we mean exactly by this, it means that from a hypergroup, under the certain fundamental relation on it, we're gonna arrive with a group. From hypergroup, we get a group. From HV ring or hyperring, we're going to get a ring. The first such relation was introduced by Koskas in 1970, and he defined this relation in this way. Beta, it will be in this way, and beta star is the transitive closure of beta. This beta star, we name it as fundamental equivalence relation on H, and H mod beta star, under this operation, we name it as the fundamental group. Koskas proved some interesting properties about this relation, and he said that it's the smallest strongly regular relation on H, such that, of course, H mod beta star is again a group. And also he said that if H is a hypergroup, then we get beta star is equal to beta. In order to understand fundamental relations, we put an example here about our hypergroup. This is our hypergroup. The fundamental relation here is the trivial one, or we can say S mod beta star here is the trivial group. Why? We can say here A is related to A, which is trivial. Also, A is related to BY because A and B, both of them, they belong to what? To A star A. So we have A to B. Also, we have A to C because AC belong to A star A. Also, we have BC. Use that all the elements in this hypergroup, they are related to each other. So we're gonna arrive at S mod beta star is the trivial group. By the way, because this one is a cyclic hypergroup, we already proved in one of our articles that whenever we have a cyclic hypergroup, the fundamental group of it is trivial. Now, after Kafka's fundamental relation on hypergroups or semi-hypergroups, Vogyuklis in 1990 introduced the fundamental relations on HV ring, and he introduced it in this way. And the operations on it, they are defined in this way. He proved that gamma star is the smallest equivalence relation such that it's the smallest equivalence relation such that we're gonna get a ring, such that, sorry, H mod gamma star is a ring. By the way, regarding the notation that we are using here, Vogyuklis, when he introduced the fundamental relations, he introduced it as gamma in this way. In other papers, you may see gamma as capital gamma, but they mean the same. Both of them, they mean the same. Okay, now we are ready to introduce hyperstructure theory and arithmetic functions. We're going to talk about the hypergroup of arithmetics, the hyperring of arithmetics, the fundamental group and ring of them. So let's start. First, let's recall what we mean by an arithmetic function. So an arithmetic function is a function whose domain is the set of natural numbers and whose codomain is the set of complex numbers, and some books, they use the codomain as the set of real numbers. Now, in 2010, Asghari and Davos, they took the set of arithmetic functions. They define a hyperoperation on this set in this way, as alpha circ B is the union of all alpha D beta N over D, where D divides N. And they prove that G under this hyperoperation is a commutative hypergroup. Sorry? Is there any problem? Are you hearing me? Please, if there is any problem, just write it on the chat box, so I'm gonna take it into consideration.
NPTELचा होता का?
नाही. Okay, still seeing the screen?
Yeah, yes, ma'am, it is visible. Professor Vijay, kindly turn off your mic.
Continue right now.
Are you getting me?
8 वीक तर तुम्ही मला एक सांगा, 12 वीक करता.
Professor Vijay, are you getting me? Yes, ma'am.
So, in 2017, we defined another hyperoperation on this group, on this set, defined as a star in a way, instead of having multiplication between alpha of D and beta of N over D, we have the plus operation. Also, we proved that this one, G star, is a commutative hypergroup. Now, in order to understand how can we deal with such hyperoperations, we put here an example to illustrate it. Here we took the fundamental, arithmetic function alpha of n equal n, which is the identity one in the sense of arithmetic functions. We took beta of n equal 1, which is a constant arithmetic function. And we're gonna find alpha star beta n. According to our definition, alpha star beta n is alpha of n over d, alpha of n over d, or alpha beta, sorry, alpha of d plus beta of n over d. Alpha of d is d, beta n over d is 1, so we're gonna get 1 plus d such that d divides n. So to find alpha star beta of 1, we're gonna substitute. Instead of n1, we're gonna get it as what? As 2. To find alpha star beta of 2, we're going to substitute instead of n2, we're going to get d divides 2. We have 2 divisors for 2 here, which are 1 and 2. So we're going to get 2, 3 here, and so on. Now, to find our alpha star beta, it will be the set of arithmetic functions such that alpha star beta, for 1, we can take it 2. For 2, we can take it 2. For 3, we can take it 2. So we're going to get gamma 1n in it. Then we can take alpha star beta of 1, 2. Alpha star beta of 2, we can take it 3, and so on. So we're going to be having infinite number of arithmetic functions inside alpha star b. So alpha star b is subset of G, and thus it is a hyperoperation. Also, we found the identity in this hypergroup. We denoted it as 0 star. We found also the identity for G circ, and we named it in this way using this symbol. Of course, these two identities, they are not scalar identities. They are just identities. Some of the results that we proved is that A of G, the set of all additive arithmetic functions, what we mean by additive arithmetic functions is that when we say to be for alpha to be additive arithmetic function, we should be having alpha m plus n is equal to alpha m plus alpha n whenever the GCD is equal to 1. To prove that this one is a subhypergroup has the distributive law. It wasn't, we did not have equality in the distributive law. We have the weaker version of distributive law. And here's our remark. It's not a hyperring. Also, after that, we characterized the strongly regular relations of this hypergroup, and we found the fundamental relation of it. We said that if we have a hypergroup, then alpha beta y, and of course here, as we said before, beta and beta star, they coincide because G star is what? G star is a hypergroup. The necessary and sufficient condition for it to be is when alpha of 1 is equal to gamma of 1. Also, we proved that G mod beta, which is the same again as G mod beta star, is isomorphic to the group of complex numbers under addition. And in order to prove it, of course, okay, just because I'm hearing some noise, so I'm thinking that there is a problem in something. In case there is a problem, I'm able to read the chat box, but according to the chat box, there is no problems. Okay, now in order to prove it, of course, this is not the proof. This is just an outline of the proof. If you want to check the proof, you can just check the paper, and I'm gonna leave the references at the end. First, we're gonna take a map from G mod B to C, defined in this way. We name it as ipsi here. Ipsi of beta of alpha. Beta of alpha, it means that it's the class of alpha. It's equal to alpha 1. Someone on the chat box, they are asking me to send the PowerPoint presentation. For sure, I'm gonna share it, and you can get it from my ResearchGate. I'm gonna share it within a couple of hours on the ResearchGate. And of course, Patty has it. She can send it to all of you. Then we're gonna prove that ipsi is a group isomorphism, and then we're gonna deduce that this will be our fundamental group. Now, what can we deduce from this theorem is that the fundamental group of the hypergroup of arithmetics is the group of complex numbers under standard addition, and of course, up to isomorphism. Okay, we are done now with the fundamental group of our hypergroup. Let's talk about the fundamental ring, our HV ring. So we proved also in 2018 that the HV ring of arithmetic functions, the fundamental relation of it will be coinciding with the fundamental relation beta star, and we get G mod gamma star. It will be isomorphic to C plus dot, which is the ring of complex numbers under addition and standard multiplication. Here we have the outline of the proof. So first, we proved that gamma star is a strongly regular relation on G star. And then we took a map chi from G mod beta star, because we are saying that beta star and gamma star are equal, and we proved it in our paper. And we proved that this chi is a ring isomorphism. Now, what can we deduce from this theorem? We can deduce that the fundamental ring of HV ring, of course, again, up to isomorphism, is the ring of complex numbers under standard addition and multiplication. Now, let's sum up everything that we discussed throughout the talk. So mainly, we were concerned about only some hyperstructures, which are the hypergroup of Marty and hyperrings. Also, we were concerned about HV structures, that they were HV groups, HV semigroups, and HV rings. We presented some applications of these hyperstructures to arithmetic functions by discussing the hypergroup of arithmetic functions as well as the HV ring of arithmetic functions. Also, we found their fundamental group and fundamental ring, respectively. There are many other types, defined types of weak hyperstructures and hyperstructures that weren't discussed in this talk, like canonical hypergroups, polygroups, semi-hypergroups, very thin hypergroup, very thin HV groups, Krasner hyperrings, hypervector spaces, hypermodules. The list is very long, so I'm not going to be able to talk about them all, but we did not discuss them throughout this talk. Hopefully in other talks, we're going to discuss them. Also, regarding relations, we just defined two relations, relation of Bogg-Euclid and HV ring, and relation of Cos-Cas for semi-hypergroups. But in reality, we have other different fundamental relations that they were defined. For example, Freni in 2002, he defined an equivalence relation on semi-hypergroups and proved that the quotient of this hypergroup or semi-hypergroup is an abelian group. Also, he proved that it's the smallest strongly regular relation such that the quotient is an abelian group. What we mean by an abelian group, it means that if we have G plus to be abelian, we need A plus B equal B plus A. Now, in our work, our relation, the one of Cos-Cas, and the relation of Freni, they coincide. Why? Because our hypergroup, if you still remember, is commutative. Now we can raise some questions. So, can we find a necessary and sufficient condition for the two relations to coincide together? By the two relations, we mean the relation of Freni that we are just talking about here and the relation of Cos-Cas. Another question, is the fundamental abelian group up to isomorphism can be considered as a subgroup of the fundamental group? Also, another example, they define fundamental group, they define fundamental. So, can we find a strongly equivalence relation R on the hypergroup or semi-hypergroup G star such that G mod R is a cyclic group? We're going to put some useful steps to answer the last question. So in order to answer this question, first we need to define such a relation in order to get the quotient is a cyclic group. What we know from group theory, that cyclic group, it's very easy to deal with. Why? Because in the infinite case, they are all up to isomorphism. They are isomorphic to Z plus, which is the set of integers under addition. And if they are finite of order n, then they're gonna be, of course, n is positive and a natural number. They're gonna be isomorphic to Zn under addition, standard addition modulo 1. After that, we're gonna use our characterization for all strongly regular relations and the characterization for G mod R to get the answer of this one. Now, the results in this presentation are from joint work with Professor Bishan Davos from Yazd University, Iran. I want to tell him hi, and I hope for him also luck for today's lecture, his today's lecture at 5 p.m. in AHA Congress. These are our references, and of course, I'm going to share them with you. And finally, thank you all for your attention. And I hope that you understood what we discussed throughout the talk. And of course, if you have any questions, please let me know, either by telling me exactly what's the question or by writing it. Thank you. Okay, any questions?
Thanks a lot, thanks a lot, Dr. Madeleine, for your nice presentation.
Thanks a lot, dear.
This presentation, it's very clear, but there is one problem is the voice is not well clear, but it's good. Thanks, Madeleine.
Thank you.
Well, thank you very much.
Yes. So I'm answering some questions through the chat box.
Hello?
Hello, I'm hearing you.
Okay. It's Aaron back. Hello?
Yeah, I'm hearing you, but I don't know whether you are hearing me.
Hello?
I'm just asking whether you are hearing me. Yes, Adesina, I'm hearing you.
Yes. My question is, the arithmetic functions you have considered, they are assumed to be multiplicative. They are all multiplicative arithmetic functions.
Please, Adesina, can you repeat the question because there was lots of noise?
I'm saying that the arithmetic functions you considered are multiplicative arithmetic functions. They are multiplicative.
Okay.
So if they are not multiplicative, what happens? If the arithmetic functions are not multiplicative, then what happens to the work?
Now, in our work, we are dealing with arithmetic functions in general, and they are not necessary to be multiplicative functions. So we are dealing with arithmetic functions. We defined two hyperoperations on them. The first hyperoperation, it was defined by Asghari in 2010 and Davos. It was notated as circ. And the second hyperoperation, it was defined in 2017 by me and Davos, and it was denoted as star. And it's, of course, these two hyperoperations, they are defined on all arithmetic functions, and they are not necessary to be multiplicative functions. I don't know whether I get your question as you want. If not, please write it because I'm not able to hear you very well. Okay, let me read some questions from the chat box. They are asking whether there is any difference between ring and hyperring. Of course, there is a difference because in a ring, we have two operations. In hyperring, we have two hyperoperations instead of operations.
Professor Madeleine, please stop presenting
I
your
hope
screen.
that Mr. Mathematics got my answer. Stop presenting, yeah. Okay.
Yeah, stop presenting your screen, right? Fine. Now it is clearly visible.
Okay, that's great. I don't know whether there are any other questions in the chat box. Most of them, they are asking for the presentation. And Mr. Mathematics asked whether there is a difference between ring and hyperring. And of course, there is a difference because in a ring, we have operations. In hyperrings, we have a hyperoperation.
Ma'am, one more question.
Okay.
Can the ring structure can further be extended? A group, ring, non-linear space, non-linear space, etc. We are expanding, no? Like that, can a hypergroup can be expanded?
Hypergroup can be expanded. We can always define different types of hyperstructures. For example, we started with group. We can define hypergroup. Also in hypergroup, we have very special types of hypergroups, like regular hypergroups, ultra-closed hypergroups. We have fuzzy hypergroups. We have many others. So always we can define such new hyperstructures.
They're extended in the topological structure.
Exactly.
What about the analysis structure? Analysis, linear space, non-linear space, like that.
Yeah. Also in analysis, they already, I forgot to mention that we have hypervector spaces. Also, we have hyper absolute value. We have hyper normed spaces. So it has lots of applications in analysis. And the things that they were defined in analysis, they are generalized using these ones, the concepts of hypervector spaces, hyper normed spaces, and hyper absolute values.
Thank you, ma'am.
Welcome. So, any other questions? Someone is asking whether there is applications for hyperstructure theory. Sure, there is. Sure, there are many. And there is a book written by Davos on application of hyperstructure theory. You may check it. Also, Vagiuklis wrote many books about applications of hyperstructure theory in different fields, like automata theory, like neutrosophy, and like fuzzy sets, and many others. Okay, so do we have any more questions? Are there other questions?
Participants, you're all welcome to ask questions.
So I'm trying to check whether there are some other questions that I did not answer. So mainly some of them they were asking about, okay, someone was asking, is there a specific reason for naming it as hypergroup and hyperring? Since hyper, we mean it to be some specific. Actually, I know why did they name it as multi-group, because the operation, we have multi-operation instead of operation. Hypergroup, I guess that they found it easier to write these ones as hyperstructures, just to notice that they are generalization of these structures. But I can search about the name if there is a specific reason to name it that.
Hello.
Hello.
Can you hear?
Yeah, I'm hearing. Yes.
I have a doubt. What is the exact difference between fuzzy group and hypergroup?
Between fuzzy, hypergroup, and a hypergroup?
Yes.
Okay. Hypergroup, we put its definition. We have a non-empty set. We have a certain hyperoperation, and it satisfies the associative law and the quasi and the reproduction axiom. Regarding fuzzy hypergroup, it's defined on a hypergroup. So mainly we are starting with a hypergroup H cert. We are defining a fuzzy set on it. And of course, a fuzzy set, we know what we mean by it, by giving each of its elements a fuzzy value. Then to say that it's a fuzzy hypergroup, it should be satisfying some relations such as mu x circ y, it should be greater than or equal the minimum of a mu x and mu y, and if it has an inverse, mu x inverse, it should be greater than or equal mu x. This is just the difference. So in fuzzy hypergroup, we have to start with a hypergroup, define on it a fuzzy set, and we can name the fuzzy set as mu. Similarly, for nitrosophic hypergroups, yeah.
Is it possible to extend hypergroup to nitrosophic hypergroup?
Already Adesina was talking in his talk about nitrosophic hyperstructures. So, and in the International Journal of Nitrosophic Sciences, we published many articles in this domain, which are nitrosophic hyperstructures. And I wrote more than one paper about nitrosophic polygroups. Already there is a paper about nitrosophic hypergroups. There are also papers about nitrosophic hypermodules, nitrosophic B algebra, and many others. Of course, this is a domain that most researchers in nitrosophy and hyperstructure theory, they are involved in and they are writing. And one of the most important researchers in this domain is Adesina. Ajbula Adesina. He's working in this domain and he's defining many relations between nitrosophy and algebraic hyperstructures.
Another question, is there any paper which is available intrinsic hypergroup?
Please, can you repeat the question?
Is there any paper which is available intrinsic hypergroup?
Is there something available? What is the something that is available?
Yes. I don't know whether any working is going on intrinsic hypergroup. I don't know. That is why I asked.
There are lots of researches done on hypergroups. There are many books about hypergroups. You might check books for Corsini, for Lirona, for Irina Christia, Bijan Davos, for Vogiuklis. There are many books about hyperstructure theory and its applications and the trends in this theory nowadays.
So what is the advantage of studying this hypergroup in real-time application? Any real-time application?
I don't know why I'm not able to hear your question. May you please write it also in the chat box so I can read it? May you please write your question?
I need real-time application of hypergroup.
You want some applications in hyperstructure theory. Okay.
Yes.
Now, if you still remember the first slides that we showed about the chemical reactions, we found many applications. We named them as chemical hyperstructures. They were applications of hypergroups in chemical reactions. We considered redox reactions. We considered also the galvanic cells, and we considered the many other reactions and proved that they define under certain hyperoperation hyperstructure. Also, we gave an example on the ABO blood group. The ABO blood group, the table that I shared in the third slide, I guess, this one, it's an HB group or a semi-hypergroup. Also, regarding Mendelian inheritance, all the cases in Mendelian inheritance, whether we have dominancy or whether we have incomplete dominance, in the F2 offspring, the table for the F2 offspring, we're going to get it as a hypergroup. So these are applications that they are related to chemistry and biology. There are some applications related to physics. Recently, I attended a conference. They were talking about applications in elliptic curves, which is a branch in number theory. There are many other applications. Also, I know that they have applications in decision making, in automata theory, and a very important application is hypergraph theory. And a hypergraph is a generalization of a graph. So these are the applications that I mainly know. But of course, there are many other applications.
Okay, thank you very much for your kind explanation.
Welcome. Any more questions?
No. I need your
Okay.
email. I need your email ID. I will talk to you through email.
Okay, sure. I'm gonna write it in the chat box, and of course, you can find me on my ResearchGate page. I'm gonna write also the
Thank you.
I'm gonna share my presentation there, so you can check the ResearchGate also. Yeah.
Okay.
Okay.
Thank you.
Welcome. Any more questions, guys?
Ma'am, I have a question.
Yeah.
Could we relate this neutrosophic with fluid dynamics?
Could we talk about neutrosophic and
Fluid dynamics. Fluid dynamics.
fluid dynamics? Actually, for nutrosophic science, I'm not through the theoretical part about nutrosophy. My domain in nutrosophy is just I'm working on applications of hyperstructure theory in nutrosophy. I guess that the best person to answer you this question is Professor Ahmed Salama or Professor Saeed Brumi. I don't know whether Saeed is still with us to answer you, or Professor Florentin Smarandash. They are like the heroes in the domain of nutrosophic science, and I'm sure that they're going to help you much more than me. But I guess there are you can find a link between nutrosophy and fluid mechanics. And of course, if we have a link between fuzzy set or fuzzy logic and fluid mechanics, so for sure we're going to have a link between nutrosophic sciences and fluid mechanics. Saeed, are you still here in order to answer her question? She's asking whether we can find a link between nutrosophic science and between fluid mechanics.
Dr. Madeleine, thanks for the presentation again. And for the question, Dr. Geita can see the Notrosophic International Journalific NSS. I think there are some paper on this, and also she must be looking to the second International Journalific Notrosophic. There is just one paper on this fluid dynamic, but it's just an initiation on this area. Thanks a lot.
So I write the journal name that to the chat, International Journal of Nutrosophic Science, IJNS.
I can answer for Geeta, madam.
Tell me, sir.
I think fuzzy differential equation, fuzzy partial differential equation, which is available. Therefore, I think we can extend the fluid dynamics to fuzzy fluid dynamics. If it is extendable, obviously we can extendable. So it is also extendable to hyper neutrosophic, easily extendable. I think so. I don't know, but it is possible.
Thank you, sir. Thank you, sir. Thank you.
I have just one information for participants. If someone know the application in a different area, it should be suggested to Journal of Notrosophic Science, and the participant will see a lot of example and application, and working also on a new field. Thanks for organization again.
So any more questions? I'm just rechecking the chat box so that I'm going to be answering all the questions. But of course, I shared my email. So whenever you have a question or you need any reference or whatever, you may just contact me via email or through ResearchGate. So again, do we have any other questions?
Dear participants, any other questions? Thank you, Dr. Madeleine Tahan, madam. We understand the notion of algebraic hyperstructure, particularly semi-high group, a quasi-group, hyperring, with suitable examples. You gave an idea to the researchers who are doing research in algebraic hyperstructure. And your talk is an eye-opening a presentation to those who want to start doing research in algebra. Thank you so much, ma'am.
Thanks a lot, Patty. As a final note that I'm gonna say for today, I want to thank a lot the organizing committee of the FDP in Trends of Mathematics. I know how much effort you put to make such an international event successful. I want to thank you again and again and again. A special thank you for you, Patty, and special thank you for Said for nominating me to be a resource person. Thank you a lot, Patty. I enjoyed working with you.
Thank you so much, ma'am. Good evening, one and all present here. On behalf of the organizing committee of 1 week international FDP on avant-garde trends in mathematics, I, Dr. M. Parimala, deem it a great honor and privilege to propose the vote of thanks on this august occasion. My sincere thanks to the management for giving me a platform to conduct this fruitful program. I thank Professor Dr. K. Shivakumar, Dean Planning and Development and Staff Affairs, Dr. S. Jagadishwaran, Professor in charge Academics, Research and Development, the Principal, Dr. C. Palaniswamy, for their constant support. My heartfelt thanks to the distinguished invitees to this 1 week international FDP on avant-garde trends in mathematics. Dr. Imran Muchandi, Alam Sai, Institute of Technology, Bandung, Indonesia, Dr. L. Shankar Ganesh, NIT Goa, Professor Ahmed A. Salama, Higher Institute of Business and Computer Science, Egypt, Professor Agbula Adisina, Federal University of Agriculture, Nigeria, Professor K.N. Raghavan, IMSC Chennai, Professor Sina Bozal, KAU King Abdulaziz University, Saudi Arabia, Dr. Rajesh Khanna, IIT Kharagpur, Dr. Madeleine Tahan, Lebanese International University, Lebanon. I also thank to you all, the distinguished professors, as you all accepted the invitation immediately, even in your busy schedule, and helped us to extend this program a grand success at your end. I am extremely thankful to Professor Said Bromi, who took part in this FTP in all means and great valuable suggestion till the end. I'd like to thank our head of the department, Dr. P. Geeta, who encouraged us to do this and gave valuable suggestions and also stood with us till the end. Without her, this could not have been possible. I would also like to thank our colleagues for their timely help. My sincere thanks to all the participants from various countries like Bahrain, Egypt, Ethiopia, Indonesia, Kenya, Saudi Arabia, Lebanon, Morocco, Nigeria, Oman, Pakistan, Syria, Thailand, Turkey, and different states all over the India. Totally 14,600 faculties from various institutions registered and attended this FTP. Once again, I thank you all on behalf of the organizing team of Avant-garde Trends in Mathematics for your great support towards the grand success of this FDP. Thank you. Thank you once again. Thank you, Professor Agbula, Said Bromi, and Madeleine Tahan for accepting my invitation. Thank you so much. Without you, this might have been that much possible. Thank you so much. Dear participants, you can just get your certificate by filling the feedback form, and you can generate the e-certificate.
So near future,
Yes. Sir, I couldn't hear you.
Near future, are you going to conduct any FDP?
Yes, sure, sir. We'll conduct another.
I'm not able to hear.
Sir, you can just see all the FDPs, which is put on YouTube live channel. You can just view it. You can subscribe, then you can get the forthcoming events.
No, no, no.
هتنقول
My question is, madam, near future,
Tell me, sir. I'm here. You tell me.
near future, are you going to conduct any other new FDP?
Yes, and not FDP, and upcoming events are there, sir. We'll be informing you every now and then.
Okay, madam.
Allah
Thank you very much, because it's a nice one. Because I have
Okay, sir. Every now and then I have a contact with you, and I'll be sending you every now and then whatever upcoming events are there, and we'll be able to do it.
Thank you very much. Thank you very much.
Okay, sir. Okay, sir.
Certificate cannot download it, madam.
Yes, Professor.
Certificates cannot download it from the link, madam.
عزبة غاية هذا طالب ديال أديسينا.
So certificates can be downloaded. So the gateway might be busy, sir. Everybody will be now downloading the certificates. You can please wait a while for getting the certificate. So half an hour later, you can just download it, sir. So at the stretch, everybody will be downloading it, and the gateway will be a problem for you.
Madam, there are only 4 options of now, madam. In that e-certificate link, there are only 4 options. So our FDP option is not available.
صح إداريا ما قاشد معكم فيه.
So in the link given in the e-certificate generation, there are only 4 options. So which option to be selected, and the FDP option is...
Sir, anybody got the certificate, sir? Dear participants, anybody got the certificate?
In the chat box, everybody is telling that
No, madam.
generation.
No, madam, create problem to download. It's
Okay,
not
sir.
downloading.
Sir, everybody will be trying to download. So please try it later.
Vita, I have got the certificate.
You got
Okay,
it, ma'am?
Yeah, I have got it.
You got a
Dear participants, you please give it time. It will be downloaded.
It is
and-
asking for the program, which program do you want to download, and also the email ID, registered email ID. It is asking.
you will have
Okay,
to
madam.
download the certificate through your registered email ID, and then you will have to choose an event. So this event is faculty development program, Avant-garde, Trends in Mathematics. You try to click on that, and then you just download your certificate. It will be downloaded.
So
Good afternoon, Parimla.
Yeah, ma'am, tell me.
Ma'am, I'm Alati from Gobi Arts College, ma'am. Due to network problem, I'm not able to receive the feedback link, ma'am. Will you please send it again in the chat box, ma'am?
Sure, ma'am.
Hello, ma'am. Hello.
Yes, ma'am.
Speaking from Kolkata, ma'am.
Ma'am.
Hello. I'm able to download the certificate, ma'am.
Ma'am, the gateway might be busy, ma'am. You just wait a minute, at least 10 minutes, 15 minutes. You give a pause, and then you try to download it.
Okay, ma'am. Ma'am, I'm having a
Because
query.
all the participants will be downloading it, the gateway might be busy.
Ma'am, I'm having a query. There it's given that select the program. So that is Avant-garde trains, no?
Yeah. That you will have to click that.
I'm clicking on that, but it is not opening. Okay, ma'am. Okay.
Ma'am,
Okay,
see,
I'll
Jayanti
wait.
ma'am got it. So
Yes,
it's just
ma'am.
wait for a while, ma'am. Everybody will be
Okay.
downloading it, so the gateway might
Yes,
be
yes,
busy now.
okay.
Okay,
Ma'am,
ma'am.
if it is not received by today, ma'am, shall I mail you?